Okay, our first video of Calc 1 is section 1.1 from our book, Functions and Their Representations. It's important to understand functions because in calculus, that's pretty much the main element we're going to deal with all the time. Taking derivatives of functions, integrals of functions, limits of functions, all these things are to come. These are all operations on functions, but in order to be able to do an operation on a function, we're going to need to just remember some basic things about a function. So the very first thing to remember is what a function is. A function is a rule that assigns to each element x in a set D exactly one element called f of x in a set E. Now these sets D and E will later become known as the domain and range of the function f. So it maps from its domain into its range. That's what this arrow here indicates. So if we were to have some element x in our set D, then f maps this element x to f of x, or maybe some y value if we wanted. And it appears that in this, arbitrary drawing of a function, there's a point z, and f happens to map z also to the same point as f of x. We could have yet another point, maybe v in here, and v could be mapped by f to this other point. Perhaps that one is f of v. Maybe we call that some value u. So typically these will be numbers over here in the set D. So it'll be f of 1 is equal to something like 2, right, on the right-hand side in the range. So real numbers on the left, real numbers on the right, or in the domain and range. So later we'll talk about one-to-one functions, onto functions, things like that throughout the course. But for now, we just have to remember that a function is just a rule that picks up an element in one set. Typically for us, that'll be a number, and it maps it to or associates it with a number in a different set. Most of the time, we'll be talking about the real numbers over here or some subset of the real numbers, and that function f assigning a number in the real numbers to another number in the real numbers here. So each of D and E will be the real numbers or a subset of the real numbers. So let's have a look at some functions we're probably familiar with, or at least some representations that we might know. So 4 ways to represent a function. There are probably more than that, but these are 4 that we'll commonly think of or come across. The least common of which is by a word description. We could describe a function in words. One function would be something like take a number and double it. So that would be f of x equals 2x, right? We're going to take a number x, right? I hand you a number x, and then you double it by multiplying it by 2, and that would be a description of it. Take a number and double it, right, is our word description. This part here actually corresponds to the algebraic formula for a function, which is the most useful representation in terms of calculus. So nonetheless, that's a familiar one to us, and that's a nice quick way to say it. So how about a second way to represent a function is visually or graphically, and this is commonly done on the Cartesian plane, graphing on the xy coordinates if we have some kind of algebraic formula to go with it. Another way to do it is by a numerical table. That's just listing input values. And each time we list an input value next to it or under that input value, we list its output value. And then lastly is an algebraic formula, which is methods that we're familiar with from algebra. That's that f of x equals 2x scenario. So here's an example of all 4 of these right here. So they ask us to consider the area for the formula for the area of a circle with radius r, and then represent this formula in each of the 4 different ways. So one way to talk about the area of a circle is to literally say area is radius squared times the number pi. So whatever the radius of our circle is, we square it and we multiply it by pi. Now, graphical representation is as follows. This is the function on the r-axis, now standing in place of x for an independent variable. The dependent variable is a, standing in place of y. So for each radius value we plug in here, we get a point or value on the a-axis that is the area of the circle with that radius. So one specific place to see is that the area of a circle with radius 0, right here at the origin, well, if we plug in 0 to this, we're going to get 0 for a, and we see that, yes, the point at the origin has a value 0 as well as r value 0. So the area of a circle with radius 0 is 0, as we would expect. The area of a circle with radius 1 would be pi times 1 squared, that's pi, right? So we'd have pi on the a-axis and a 1 on the r-axis. So this is a fairly steep quadratic curve. Okay, another way to represent it is through a table, right? Here are a list of circle radii, values the radius of a circle could be. If the radius is 1, then the area is pi. If the radius is 2, the area is 4 pi. Radius is 3, 9 pi, and so on. We could even put fractions or irrational numbers into this table, but it's a little bit harder to express those. Now, what's the most concise and complete way to list a function or describe a function, or perhaps one of the most useful, especially in terms of algebra and calculus? That's the following, right? Even before we got here, we kind of wanted to have a look at this formula so we could remember what the graph might look like. That's the way we got to that anyway, most likely. But we could have taken this table and also translated it by points to this curve and then drawn a curve that more or less fits that and catches the trend. But this is the more exact version down at the bottom. And this is most of what we'll deal with throughout the course. The function will be usually in terms of y equals f of x, but it's okay for the variables to get mixed up a little bit, right? This is a as a function of r. So we might write something like a of r, the area as a function of the radius is pi r squared. So in this way, the area is shown to depend on the radius r, and the way in which it depends on it is via this formula. So those are our four most common representations of functions and things that we'll see in the course. Let's move on to testing whether or not a graph is actually a function. And that's the vertical line test, right? So a function or a rule describing a set of points from one to the other that's described as a graph, or in other words, a graph of what might be a function, can be evaluated as to whether or not it's a function through the vertical line test. Remember that a vertical line test, in the vertical line test, I'll get into the details of this example in a moment, but no vertical line should intersect the graph of the curve in more than one place in order for this curve to be a function. It looks like this example passes the vertical line test, and that is actually the case. So let's have a look at what they're actually having us do here. So they're giving us a function. They say determine whether the relation for x and y given below is a function. So if we're not sure if something's a function, we typically call it a relation. So in that way, it says that y is related to x via this rule. So if we have an x, it puts out a value y based on this formula. What we want to be sure of is that if we put in 1x, we get back one value for y. If we put in one value of x and we get two values of y, well, then we don't have a function. We're not sure what x maps to in terms of y values because it goes to two different y values. That's not acceptable for a function. However, it is okay for a relation. We won't really work with relations in the course, but it's just good to realize. So the first thing we have to remember is, well, how do I graph this curve? What does the graph of this thing look like? So remember from an algebra course that we start with its root function or parent function, which is the square root of x. So y equals square root of x. And we sketch that graph first. And it looks more or less something like this, sort of a half of a laid over parabola. Y equals root x. Okay, now this thing is shifted along the x-axis, and that's because there's an x minus 3. If we had an x plus 3 or 3 minus x, we'd have some similar situations going on. In this case, the x is a positive x, right? It's not 3 minus x, so it's not translated as well. It's not reflected, rather. In this case, it's just shifted or translated by 3 units. Now, the easiest way, I think, to figure out where one of these graphs is shifted to is to look at where the new 0 is. In other words, how do I get a y value of 0 from this function right here, the square root of x minus 3? Well, that's obvious. When x is 3, I have 3 minus 3 under the radical. That's 0, and the square root of 0 is 0. So that tells me that at 3, when I plug in 3, I get a y value of 0. So this point 3, 0 is this new sort of beginning of this curve, right? The new fixed point of the curve or stopping point of the curve. And that corresponds to what originally the 0 was. When we plugged in 0 for this function at x, we got 0 for y, and we were at the origin. Now to get that same point on the red curve, or the curve we're actually trying to graph, we see that it's at 3, 0. And then everything else shifts along with it, right? What you might remember from an algebra class is that this is x minus 3, or you should remember this. This tells us that we shift 3 units to the right. So we just take this curve, shift it 3 units to the right, as we see down there on the x-axis, and we'll have the exact same curve, another copy of it, but 3 units over. And then we can test to see whether or not it's actually a function. And we did so, and I've already pointed out that the vertical line test, we look at the function, we maybe sketch a few vertical lines or imagine a bunch of vertical lines going through it. And if it appears that no vertical line passes through this curve more than once, then it's a function. Now, if this thing had another leg below it, something like this, then clearly it would fail the vertical line test, right? This would not be a function because it would strike it here and here, and that would be the same vertical line crossing through this curve in 2 places. So in that case, it would fail the vertical line test and not be a function. But we don't have such a leg, and this thing actually does pass the vertical line test. So there we are. Well, lastly, they ask us to find its domain and range. The answer is already given at the bottom, but let's remember what that is. The domain is the set of all values along the x-axis that we can plug into this function and get a real value y back. So all the places where this function is defined is another way to think about it. Well, why didn't 2 or 1 or 0 make this domain answer? Well, that's because we cannot take the square root of a negative number. If we plug in 2 to this square root, we have 2 minus 3, we have the square root of -1. Well, that's an imaginary number. We don't get a real number out. So for us, we're just going to say that that function is undefined there. Or another way to look at it is you realize that our curve, there's no red curve above this zone of the x-axis. And there isn't any curve until we get to x equals 3. And then after that, we have a red curve above the x-axis for the whole rest of the real number line to the right. So we have 3 to infinity as our domain. Okay, now the range is all the set of all y values for this function that we can obtain. And we see that, well, there's no way to get a negative number out of this, right? We're going to take the square root of a positive number and get a positive each time. Remember, we're not solving for y squared equals something. This is literally given to us as a function that's a positive square root of something. So we're always going to get positive numbers out, or it'll be undefined over here. So since we always get positive numbers out, the least this can be is a 0. 3 minus 3 is 0. Square root of 0 is 0. So this is our lowest point on the y-axis, but we obtain every other value on the y-axis eventually. So this is 0 to infinity for the range. So the domain are the x values and the range of the y values. Or domain is the horizontal axis and the range is the vertical axis. So let's continue in a similar fashion. Some functions are piecewise defined. Remember, we've probably seen this in an algebra class. So this means that the function just has a slightly more complicated set of definitions for it, and it's defined by wherever you are in the domain of the function, or whatever the x value is in the domain of the function. So one of the most famous piecewise defined functions is the absolute value function. So x being some number, the absolute value of x is either negative x or it's positive x. Okay, and we'll talk about why that happens in just a minute. So in order to know which of these two to choose, we have to look up which condition is satisfied by this number x that we plug in. If x is less than 0, then our answer or our output is negative x. In other words, if x is a negative number, then our output is negative x. Now, if x is a positive number, then our output is x. That sounds like the absolute value, right? If the number is positive, then we just write the number down. If the number is negative, you make the number positive. Well, how do you make it positive? You put a negative in front of it, and that cancels out the other negative. Let's see this in action real quick before we do any of the things the problem's asking us about. So I'm going to look at example evaluations of this. So if a is less than 0, then the absolute value of a should be negative a. And you might object to that and say, well, that's a negative number. It's not actually, right? So let's take, for instance, a being negative 3, or x is negative 3 in this case. If we're going to take the absolute value of negative 3, the way the piecewise formula works is it says, okay, negative 3 is less than 0. So that means that my function tells me to write negative 3, right? That step right there is actually our negative x step, right? So this is a negative, a negative a step is what I'll say, right? Well, a is negative 3. Maybe I'll call this thing a to clarify that. And negative 3 is less than 0. Well, this negative corresponds to that minus sign, and a is equal to negative 3, and two minus signs together cancel out and make for a positive sign. That's one way we can define the absolute value in terms of algebraic signs. So if you give the absolute value a negative number, what it does is it multiplies that negative number by a negative 1, or a negative sign like this, and that cancels it to give you a positive 3, or a positive number in the end. And that's how it goes about making negative numbers positive. It just multiplies by a minus sign. Okay, now the version that we're more familiar with and more comfortable with is probably this one. What's the absolute value of 5 halves? Well, 5 halves being b, right, corresponding to all this, b is greater than 0. And right, 5 halves is greater than 0 in this case. Well, this just says output the number itself, and we get 5 halves. Okay, so that's the one that's easier, right? X is 5 halves. 5 halves is greater than 0, so the answer is just 5 halves. So there we go. That's how the absolute value more or less works. Now, to graph this function, we just have to note this. Well, when x is greater than or equal to 0, it has value y equals x. Well, what is y equals x? That's our identity function. That's our most basic algebraic function of all, right? Y equals x. If you give this function the number x, it outputs that exact same number because y is equal to that x value. On the left-hand side, y equals negative x, from x less than 0 to the left. So moving this way, right, from 0 to the left. So this is y equals negative x. So all we've done here is graph the line y equals x along 0 to infinity. And then we graph y equals negative x from negative infinity to 0. And it turns out it makes this V-shaped graph that we're probably familiar with from algebra. But nonetheless, here we are interpreting the definition and the graph of absolute value of x. So lastly, there's a question of the domain. Well, the domain is a set of all x values that we can plug into this function and get back a real number. Well, x is less than 0, we have a definition for. And then x is greater than or equal to 0, we have a definition for. So it looks like all real numbers. Well, the set of all real numbers in interval notation is negative infinity to infinity. So there's our domain. Our range is the set of all y values that are attained by this function. Well, the absolute value of x never spits out a negative number, and as low as it goes is 0. When x is equal to 0, it outputs 0, right? Outputs x, which is 0 in that case. So there's our lowest value here. So y is 0. So, and it looks like it obtains every y value above that. So it goes from 0 to infinity in interval notation, and that's its range. Oh, one thing to be careful of, we should include 0. The function actually attains the value 0, so we use a closed bracket there. Notice we never use closed brackets on the symbols infinity or negative infinity because we don't technically ever include those numbers because they're not actually real numbers. They're just sort of a concept, a symbol for a concept. So that's a domain range of a piecewise function and its graph. Continuing with functions, let's talk about their symmetry. So functions have different symmetries, right? And in our case, we'll talk about even functions, odd functions, and there are functions that are neither even nor odd. So an even function satisfies this property. F of negative x is equal to f of x. So if we plug in a negative x, it's the same as plugging in a positive x. Okay. Odd functions have this property. F of negative x is equal to negative f of x. Notice there is a difference in those two things. I mean, you've worked on this in an algebra class before, so this should just be review. But this, in some sense, we think about this as passing the minus sign outside of the function's argument, right? It goes from f of negative x to negative f of x. So this is our odd symmetry. Now, a function that has even symmetry, such as, in other words, satisfies this property, is symmetric along the y-axis. So in other words, it folds along the y-axis. So this curve right here that I've drawn, if we folded it along this y-axis, we'd see that if I had drawn it perfectly, both these sides would meet up and match to each other. So it wouldn't matter if we put a negative x or positive x, we still get the same value up here. So that is our even symmetry. And then odd symmetry is symmetry about the origin. We'll see an example of that down below. So the example here asks us to determine whether each function below is even or odd, then determine which kind of symmetry each function has. So remember, the game for this is to write the function f of x down, or take the printing of it right here. We have f of x equals x squared plus 1. We're going to do a check. We want to see f of negative x. We do that one first. So f of negative x, everywhere there's an x in my formula, I'm going to replace it with a negative x. And what happens when I do that? In this case, I see that negative x squared becomes positive x squared, because a negative squared is just a positive. So that negative sign in front of the x squares, and we have positive x squared. There's no x in the plus 1, so this just stays as is. We end up with x squared plus 1. Now, before we run any checks, let's look down below. The other version of this, the other thing we will always write down is negative f of x. Okay, this is where we just take a minus sign and multiply it by our whole function, x squared plus 1. So x squared plus 1 times negative 1 makes this negative and makes this negative. So we have negative x squared minus 1. Now what we check is this. We check to see whether or not this is equal to this. If it is, f is even. We also check to see whether this is equal to this. If that's the case, then it's odd. If this is not equal to either of these, then it's neither. Okay, in this case, we see that it matches the one above. So this tells me that f of x is equal to f of negative x, and the function f is even. Okay, and that's what we've concluded over here with our reason why. Okay, so x is not odd because this is not equal to this. Right? So we know that x is not odd. So since f is even, f has y-axis symmetry. It folds onto itself across the y-axis. So the last thing to maybe mention is what, oh, we're going to check the last one. Sorry, the second part of this. So f of x again is given. We want to know if it's odd or even. We first write down what f of negative x is. So we replace x with a negative x everywhere in this formula. So there's an x cubed here. So I do 2. And then instead of an x, I put a negative x in parentheses and then cubed. Right? Everywhere there's an x in this formula, I'll make a little bubble with parentheses and I'll plant a negative x in there to come up with this function. Now there's no x in the 4, so it just ends up being plus 4. So this comes out to 2 times negative x cubed plus 4. So this is, when we cube negative x, we get negative x cubed times 2. So we have negative 2x cubed plus 4. Is this equal to f of x? No, it's not, because of the negative in front of the 2. Now, the other thing to do is we'll write down negative f of x, and we'll check to see whether or not the function's odd. Since this didn't work out, it's not even. So negative f of x is where we just multiply the whole function by a minus sign. This is negative 2x cubed minus 4 now. Does that match f of negative x? In other words, are these two things equal? Nope, it doesn't, because of the plus 4 and minus 4. So this function is not odd. It's not odd or even, and it's not odd, so it's neither. Functions don't have to be odd or even. They just might be odd or even. Oftentimes they'll just be neither. So that concludes our work on the example. Just by the way, odd symmetry has symmetry about the origin. And what that means is if you take one section of the curve and you rotate, if you take the first quadrant and rotate it to the third quadrant, remember this is the first, this is the third, or if you take the second quadrant and rotate it to the fourth quadrant, then the function will match up. And in this case, if you see that we rotate quadrant 1 to quadrant 3, we get this thing that matches up. Y equals x cubed is a great example of an odd function. Of course, you've seen all of this in an algebra course. It just doesn't hurt to review a little bit of it because it'll come in handy later for us. Increasing and decreasing. Again, another concept that we've seen, but worth a quick definition or review of. A function f is said to be increasing on an interval I if f of x1 is less than f of x2 whenever x1 is less than x2 in the interval I. Okay, so that's a whole mouthful, right? Let's think about it this way. These are our y values. This one is less than the next one. X1 is less than x2, right? So as we increase from x1 to x2, our function increases from f of x1 to f of x2 to a larger value. What that tells me, we can see it down in the photo below, is that where this x1 down here, and this is f of x1 on the curve, and then x2 is here to the right, larger than x1, and f of x2 is up here, we see that f of x2 is greater than f of x1, or vice versa, f of x1 is less than f of x2. In other words, as we go to the right and these values go up, we're increasing. Okay? And similarly for decreasing, the only change is this. We swap this inequality right here. We still go in order from x1 less than x2, right? So we're thinking about moving from left to right, but in this case, our function values go downward as we go from left to right. So f of x1 is greater than f of x2. And if that's the case, then we're decreasing. So we can see in the example here, they ask us to determine what intervals f of x equals the absolute value of x is increasing or decreasing. Then we can see that it's decreasing from negative infinity to 0, and it's increasing from 0 to positive infinity. And that's exactly what we've written down below. So there we are. It's pretty much as it looks, but implementing the definition is a little bit trickier, but it's good to understand this technicality because lots of things will be defined in similar manners as we progress through the course. For now, it might be difficult to see that, but we'll get more and more used to the notation as we progress. So that's it for functions and their representations in terms of, well, simply this lecture. There's more in the book to see, so practice the examples. Remember that the examples and exercises listed in the beginning of this are test bank problems for the course. So these are questions that might show up on exam 1, or when I go to write an exam, I'm going to pull questions from these sets of problems right here. So that is the contract between you, the student, and me, the instructor. So it's your obligation to practice all of these examples and exercises in order to know this material to be ready for possible exam. So that's it for section 1.1, and we'll move on to 1.2 after this.